Hey everybody, this is Mr. Lauer here. If you're watching this video, it's probably because you missed class on Monday, November 1st. And in this class, we proved a couple theorems. So what I've asked you to do is to kind of go through those sections in the book. And after you've done that, I think you'll have some good background information to come back and watch these videos. So the information that you're going to need here is on 3 pages of your textbook. So this is on page 185, the beginning of this section 4-2. And the first theorem that we proved in class was this theorem called the angle-sum theorem. Angle-sum theorem, or theorem 4.1. So we did this proof in class, or we went over this proof. And what I'd like you to do here is copy down the angle-sum theorem and the proof that goes with it as well. I will come back in just a second and kind of walk you through that proof, or do maybe my own version of that proof so you can understand what's happening there if you have any questions. But start there because I think there's a lot of good information there. Okay. On the next page here, you're going to learn about the exterior angle theorem. So there's actually 3 theorems here. 4.2 you're going to look at in your homework. But the other one we did in class was this one here, this exterior angle theorem. So what you should do here is define these 2 terms, exterior angle and remote interior angle. You may want to jot down this picture to help you. You're also going to write the exterior angle theorem itself, what the theorem says, what it means, kind of go through that. And then there's a proof here as well for that. And this is a flow proof. Okay, and this is on page 187. The proof is on page 187. On page 186, right before that, was the theorem itself and the definitions for exterior angle and remote interior. So I would go through basically pages 185 through 187 if you missed class today. Read through those. Make sure that you kind of jot that stuff down. Everything that we did in class, all the things that we talked about, are listed in this assignment post or that I did for the notes. Okay, but we're going to go ahead and take a look at those proofs together because I think it may merit a little bit of explanation there. Okay, so the way we wrote this out in class was we were talking about the angle-sum theorem first. We wrote the theorem. We also identified the if and the then, right? So this is a little bit tricky to pull this out of this statement, but basically we're talking about if we have a triangle, then the sum of the angle measures of that triangle is 180. So I drew my picture, I have my given and my proof statement, and this is set up very similar to the one in your textbook, just so you can kind of match it. Now there's a couple important ideas in here, and there's actually a new idea here that you've never seen before in a proof, and that's using a construction in a proof. Okay, so I'll walk you through that in step 2. Let's go ahead and start out with step 1, and in step 1 we're just going to state the given. The given's pretty basic. It's just that we have a triangle and we named it ABC in this case. Okay, now the step 2 requires a construction. So you may be wondering why this angle A is also labeled angle 2. The reason why is we're going to construct a parallel line. Okay, so what we're going to do here is we're going to construct a line that's parallel to this line, the bottom of the triangle, CB, and that goes through A. Now we actually did this construction last week in class. Remember, we took a point and a line, and we basically copied an angle, copied this angle up here, and we were able to show that we could construct parallel lines through a given point. We also had a postulate called the parallel postulate that said for every line, like CB, and every point not on that line, like A, there exists exactly one line that's parallel to CB and that goes through A. And so what we're going to do here is we're just going to draw that line, and we have our experience with constructions to tell us that that's totally possible. Okay. While I'm at it, I'm just going to go ahead and extend CB. Now the segment CB is the bottom of the triangle, and that's fine. But if we wanted to extend that out, we would get something like this. So now we have parallel lines. I'm going to mark them parallel using my little symbol for parallel here. Okay. And I'm going to start stating that in statement 2. So what I've done, oh, sorry, one more extra thing. I'm going to add some labels here. So we're going to call this line XY. We'll just give it a couple points. And we're going to label these angles that it created as well. So 1, 2, and 3. All right. So how we're going to do this is we're going to say that we're going to construct, sorry, let me go back. We're going to construct line XY in such a way that it's parallel to line CB, or you can say segment CB, since that was the part of the triangle we were dealing with, right? So segment CB, and also, in addition to all that, it needs to go through point A. Okay, now you may be wondering how we can justify that, right? Well, if you can show that you can do a construction without any specific angle measurements, with only using a compass and a straight edge, basically something that makes lines and something that makes circles, then you have basically shown that you can, I don't know, kind of construct that shape anywhere you need to. We also have that parallel postulate that we use to say that there's only one line, like XY would be the only line that goes through A and is parallel to CB. So what I'm going to say is I'm going to say parallel postulate. I'm also going to put a comma here and write construction, because we talked about how to construct a parallel line through a point last week. So that's slightly different than what it says in your book. It's pretty much this statement is the same, but I just added this little idea about construction, since in Euclid's Elements he uses constructions as some of his justifications. Okay? All right. Now, let's kind of talk about this big picture, and then we'll go from there. Think about this for a second. 1 plus 2 plus 3. If you took the measure of angle 1 and the measure of angle 2 and the measure of angle 3, and you added all those up together, what would it be? Well, if you notice, they form a straight angle, like all three of them together form this straight angle XAY. And since the measure of angle XAY has to be 180 because it's a straight angle, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 kind of need to add up to 180. Now there's multiple ways to show that, but one of the ways that we usually do that is with linear pairs, right? When we see a linear pair, we're like, oh, supplement theorem. If they're a linear pair, then they equal 180. The problem with that is that this is not a pair of angles, it's 3 angles. And so one of the things that we do is we kind of we force this 3 angles to actually look more like 2 angles, and we kind of go from there. So step 3 here, I'm going to say, is that the measure of angle 1 plus the measure of angle CAY equals 180 degrees. Okay, so let's kind of break that down. Here's the measure of angle 1 right here. Sorry, here's angle 1. Right? Now we could call that angle 1, we could also call it angle XAC if we wanted to, but we're talking about this guy right here. Okay? Now we want to make a pair with that angle, and so the other angle that I'm using is this full angle all the way around here. Right? So it's like these 2 lines. And I don't want to call that angle 2 or angle 3 because angle 2 and angle 3 are smaller. I'm going to call that angle CAY. So I basically just forced a pair. This pair, angle 1, and this other angle here. So angle 1 is right here, and then angle CAY is right here. Okay, and I can use supplement theorem there because that actually is a linear pair. Okay. Okay. Now if you look at the theorem in your book, it actually takes this this idea and it breaks it up into 3 separate steps. I think it kind of makes sense to combine them, but I'll leave that up to you. So if you look at the proof in the book, see if I can get it in there. They got 1 and 2, that's the same as us, and then their steps 3, 4, and 5 are basically kind of like all the same idea. They all go together. So they like kind of break it up and they say, look, angle 1 and angle CAY are a linear pair, and then they say, therefore they're supplementary, supplement theorem, therefore they add to 180, definition of supplementary angles. So these 3 steps, oftentimes the way we do it in class, just to kind of like save a little bit of time, and I think we all kind of get the idea. When we see a linear pair, we immediately think they add to 180, right? We've talked about that many times. So I just combined these 3 steps, 3, 4, and 5, into kind of one step. And really the key idea there, I mean, there's definition of linear pair and there's definition of supplementary kind of embedded in there, but really the idea here is this idea. If 2 angles form a linear pair, they're supplementary, right? We know what a linear pair is, we know what supplementary means. This is a theorem that we proved called the supplement theorem. Okay, so that's kind of what's going on there in my proof, and that's the way I did it in class as well. All right. Now, what we want to do is we want to say 1 plus 2 plus 3 equals 180, and I'll explain why in a minute. We don't kind of know why just yet, but that's where we're headed. And we can do that. We're just going to say, well, isn't CAY just 2 plus 3? This full angle here, CAY, is just angle 2 plus angle 3. And that is the angle addition postulate. The 2 smaller angles, 2 and 3, that form angle CAY, the measures of those 2 smaller angles add up to the measure of the bigger angle CAY that they form. That's the angle addition postulate. So measure of angle 2 plus measure of angle 3 equals the measure of angle CAY. Okay, and again, that is the angle addition postulate. All right, and so now what we can do is we got 1 plus CAY is 180, but CAY is 2 plus 3, and so I can replace this CAY with 2 plus 3. So it's going to be the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. Okay, and that's just a substitution. Substitution property of equality. Okay, now that's actually the first big step of the proof. I can kind of break this proof down into 2 main sections, and the first main section is to show that 1 plus 2 plus 3 equals 180. Now we kind of already talked about that. They combine to be kind of the straight angle AXY or whatever, and the measure of that straight angle is 180. So again, there's multiple ways that you could maybe justify that, but if you want to use a linear pair, you have to you can only do 2 angles at a time, right? I can't use a linear pair or like supplement theorem idea with more than 2 angles, because pair means 2. Okay, the next part of this proof is actually to basically take this guy and replace angle 1 and angle 3 with angle C and angle B. Okay, I know that 1, 2, and 3 are equal to 180. What I'm trying to show is that C, 2, and B are equal to 180. Right, that was kind of the game. In order to do that, we use an idea that we proved last week, and that idea is the alternate interior angles theorem. So you don't have to draw this, but I'm going to kind of off to the side here just draw part of this shape. Okay, so imagine these are my parallel lines. This is XY, and this is line CB. Okay, I'm just sketching here, so I'm sorry they don't look super parallel, but we're going to assume those are parallel because they're in our picture. Okay, now let's say that we add AB to that. Right, so here's A. Okay, well, if we continue that line, what we have here is 2 parallel lines cut by a transversal, right? And in that case, we know the alternate interior angles are congruent to each other. So this, in our picture, was angle 3, and this guy right here, this angle right here, we're calling angle B. And so these 2 angles right here, angle 3 and the one we're calling angle B, have to be congruent by the alternate interior angles theorem. If these 2 lines are parallel, which they are, the alternate interior angles must be congruent. The same is true on the other side of my triangle, because I also have this line, right? So let me just finish. Imagine this is the other side of my triangle. Okay, now imagine that this is this part right here, CA. Right, and of course I have XY floating around out there, and I have B, but it doesn't matter. This is the transversal that I'm talking about. CA is actually a line that makes a transversal with these 2 parallel lines. Okay, so what I know is that the alternate interior angles, these 2 guys, are congruent to each other. And in our picture, we're calling this one angle 1, and this one's angle C. So I know that angle 1, this guy, is congruent to angle C, and I know angle 3, this guy, is congruent to angle B by the alternate interior angles theorem. So that's an important idea. And you may have been wondering, like earlier in the proof, why did you construct that parallel line? Why do we need it? Why are we creating extra angles that we didn't start with? Well, the idea is we really want to be able to show that this thing is true by alternate interior angles theorem, which requires a parallel line. So we constructed one. Okay, so let's go from there. So line 6, we're going to say that angle 1 is congruent to angle C. Right, these two guys are alternate interior angles. And then we're also on the same line going to say that angle 3 is congruent to angle B, because those are also alternate interior angles. Okay, now I'm pretty much set up to substitute, right? Like remember, I want to show that C plus 2 plus B, the three angles of the triangle, add up to 180. I already know that 1, 2, and 3 add up to 180. So if I can just replace 1 with C and replace 3 with B, we're good to go. The last thing that I need to write before we can do that is I need to change these congruent statements. Sorry, I'm trying to talk and write at the same time. I'm changing these congruent statements to equality statements so that I can use the substitution property of equality. So measure of angle 3 equals the measure of angle B. Okay, so measure of angle 1 equals measure of angle C. Measure of angle 3 equals the measure of angle B. And that's the definition of congruent angles, or the definition of congruence. Congruence just means equal in measure. All right, so my final step is just to take step 5 and rewrite it, but instead of writing angle 1, measure of angle 1, I replace that with measure of angle C because they're equal to each other. And then I add that to measure of angle 2, which is my next angle, and then I add that to measure of angle B, which I'm replacing 3 with because they're equal to each other. And all that has to add to 180. So I'm rewriting line 5, but replacing this with C and this with B because we've shown that C is congruent to angle 1 and angle B is congruent to angle 3. And that is another substitution right there. Okay, so that's kind of how that proof goes. It's the first one where we add an extra line. We call that an auxiliary line. We can do that when we've shown that we can do that construction, right? And also we have a postulate saying that there has to be one, and exactly one, line that goes parallel to CB that goes through A. Again, you'll see that proof right here on the bottom of page 185. Okay, the difference is the one that they did is 10 steps instead of 8 steps because they broke out our step 3. They used 3 different steps to show it. So if you want to do that, you can totally do that. But as far as our proofs in class go, I'm going to say that if you see a linear pair, you can jump right to the fact that they add up to 180. I think that kind of makes sense. We've been using that for a long time. So that's that first proof. Okay. All right, the second proof requires a little bit of background work because we have to know some definitions. So in class, this is kind of how the notes looked. We we wanted to do the exterior angle theorem, but we first defined exterior angle and remote interior angle. And those are actually in your book, just kind of on the next page, and they're kind of towards the bottom. So just a little comparison here. Down here at the bottom of page 186, we have those 2 key terms right there and a little picture that's showing you what they look like. So you can use those definitions, add them to your notes, draw that picture, add it to your notes. Here's the theorem itself, exterior angle theorem, write it out, add it to your notes. And then the proof of that theorem is over here, okay? So there's a flow proof. We're going to do a flow proof as well. I'm going to make mine kind of similar to this, but I'm going to take a few liberties here, and you're welcome to do the same. So hopefully you've already read through this and that logic or that reasoning makes sense, but if you're a little stuck, you're not exactly sure what's going on there, I will walk you through the proof the way that I did it in class. Okay, so I again have exterior angles and remote interior angles definitions. If you want to pause the video and write those down, you can. I also drew my little picture, and so angle 4 is my example of an exterior angle. I just extended the side of this triangle to get my exterior angle, angle 4. And then for angle 4, the 2 remote interior ones are the ones that are inside the triangle, but they're like not connected to 4. They're not adjacent to 4. So 4 is my exterior angle. 1 and 2 are the remote interior angles for angle 4. Okay, now the exterior angle theorem says that the measure of the exterior angle, in this case 4, has to equal the sum of the measures of the 2 remote interior angles. So the way I drew my picture here, I want to prove that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. And this is a 1, by the way. So I got my given. Basically, the given is just I got a triangle with an exterior angle, and this is what I'm trying to prove. Okay, so let's brainstorm here together. First thing I would do is take a look at angle 3 and angle 4. You may notice that they form a linear pair. You also might remember that we have the supplement theorem that says if 2 angles do form a linear pair, that they're going to be supplementary. And we know that that means they are going to add to 180. So that's a key idea. So measure of angle 3 plus measure of angle 4 equals 180. We also just proved a little bit earlier that angle 1 and angle 2 and angle 3 have to add up to 180 because of the angle sum theorem. So if 1 plus 2 plus 3 is 180, and 3 plus 4 is 180, then 1 plus 2 plus 3 equals 3 plus 4. Now, of course, we need to throw some measurement like in there, and we need to make sure it's all nice and not too sloppy. I kind of stated it in a shorter way just because I wanted to get a point across. But that's kind of where we're heading in the proof. All right, so let's start off with this triangle and this exterior angle. Okay. Now I'm going to go just left to right, at least to start out, just because that's kind of the space that I have here. The book, it's going to go top to bottom, but that's okay. Doesn't really matter in a flow proof. So I'm going to start out with my given, and that is that angle 4 is an exterior angle for the triangle ABC. Okay. Now that idea, the exterior angle and the triangle, actually result in kind of 2 different trains of thought here. One of them is about the linear pair, and the other one is about the triangle. So we know that the measure of angle 4, measure of angle 3 plus the measure of angle 4 equals 180. The question is, how do we know that? How do we know that from the picture? Nothing about that picture, nothing about the given said anything about supplementary angles, right? Well, we got a linear pair, right? And we know linear pairs are supplementary. So that is the supplement theorem. Okay. Now again, in your book, they've dragged that out into 3 different steps. And in the past years, I've made students write those steps out all independently, but I think what happened is that just made it more frustrating for everybody. So I'm going to let you condense those steps, but just to point out, the book's going to not condense those, and I'll point that out when I show you the book proof. All right, at the same time, we have this idea about the triangle. So that's the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 has to equal 180. And that is the angle sum theorem that we just proved. We proved earlier in the notes that the measures of the angles of any triangle add up to 180. All right, now notice I have 2 angles that add up to 180 and 3 other angles that add up to 180. And so what I'm going to do here is I'm going to put these back together with a substitution. I'm going to say that means that the measure of angle 3 plus the measure of angle 4 has to equal the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. If these 2 angles are equal to 180 and these 3 angles are equal to 180, then the sum of these 2 is equal to the sum of these 3. That is a substitution property of equality. Okay? Now remember, our goal was to show that the measure of angle 4 was equal to the measure of angle 1 plus the measure of angle 2. But we have these pesky measures of angle 3 out there, right? And so what we're going to do is the same thing that we've done in many other proofs, is we're just going to subtract the measure of angle 3 from both sides. Sometimes in the textbook, it will mention or say something like the measure of angle 3 is congruent to the measure of angle 3, just to establish that we're subtracting the same number off of both sides. And sometimes it does that in earlier proofs. And if you want to do that, that's okay. I'm going to go straight to the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2, just by subtracting the measure of angle 3 off from both sides. So when I do that, I'm using the subtraction, sorry, not substitution, the subtraction property of equality. And that's the proof, okay, in a nutshell. Now you can make it more detailed. You can even make it less detailed. I'm trying to pick a medium level of detail for you guys to get through, because when you start adding lots and lots of steps, it gets a little bit more confusing. So let's compare that to the one in the book, okay? This is their flow proof. So they started with a triangle. Now our given was a little bit different. I said, not only do I have a triangle, I have this exterior angle. And so, I don't know, there's a little bit of variation on like what you can assume from the picture, or what you will assume, or what you have to state. So that's a little bit different in our proof. That's okay. But notice they have the two triangle ideas. They have the idea that the sum of the angles of the triangle add to 180. They have the angle sum theorem. But they also have the idea that the linear pair here adds to 180 as well. Now, like I said, they do that in 3 steps. They start by saying you have a linear pair by definition of a linear pair. Then they say that the two angles of the linear pair must be supplementary. Then they say that the supplementary means that they add to 180. And so I'm just kind of like taking all these 3 ideas and kind of putting them together and saying the main like idea there is this. If 2 angles from a linear pair, they're supplementary, and we are calling that the supplement theorem. Okay, so that's kind of the central idea of these 3 steps, and I'm just kind of combining them, all 3. Okay, when you have those 2 statements, though, the 2 statements where the sums of the angles equal 180, you got the 3 angles of the triangle and the 2 angles of the linear pair, both summing to 180. You do that substitution, so you have the 3 angles of the triangle equal to the 2 linear pair angles, and then you just subtract out the angles that you don't need. All right, those 2 guys. And you end up with what you're trying to prove. Okay, so essentially the same proof, flow proof. Mine's a little bit different. It's a little bit maybe more streamlined. I combined some ideas. The given that I started with was slightly different, but the main ideas of that proof are basically the same. Okay, so those are things that I want you to have in your notebook. Those are fair game for a test. So if I ask you, you know, hey, what's the justification for this step of the exterior angle theorem proof? I want you to know that. Or, hey, how do we justify this step when we prove the angle sum theorem? Those are things that you need to know. So if you need to, go ahead and study those proofs or rewrite them out a couple times if you need to get those ideas, because you'll be responsible for those in future quizzes and tests. Okay, those are the 2 main theorems for today. Angle sum theorem and exterior angle theorem. You have them both. You're going to use those on your homework. So it's important that you understand them. It's important that you can improve them, that you can prove them, so that you can apply them on the assignment. So thanks for watching. I hope that helps you get caught up. You'll now go to the homework assignment for today, which is a worksheet called Angles of Triangles, and there's a video there in that assignment for you as well. Thanks for watching.